Okay, we're recording.
Okay, no pressure. Cool. So this is a little demo of an idea to speed up Git clones. It only works for full clones, and the idea is to do less computation on the server and just stream data from disk. First, let me show what the normal situation looks like. I have a gitlab.git here, and that is the thing that we're going to be cloning. And this is my clone command, so I'm going to be cloning into test.git. I'm going to nuke that and then do a full clone using no local, which means we simulate what happens during a normal clone over the network, because otherwise Git uses other smart optimizations. So this is the baseline. So what you're seeing now is that the server side is trawling through the repository to figure out where all the objects are it's going to send. I'm just going to let this run a little bit. I'm probably not going to let it finish, but I just want to, it doesn't make sense to do this demo and not see what the before and after is. So the before takes a while.
And this is iterating through all the objects it needs through from the history you are cloning now. So for all the refs you want, it goes the full tree back and like marks all the objects you want.
Yeah, when you do a full clone, normally that defaults to branches and tags. So first it gets a list of all the branches and tags, and then those are commits and tags in a tree, and then it walks down the tree and finds everything that is reachable from there. And then it does this compressing stuff. So I think I've made the point that this takes time. So what I can now do with the demo is that I can create, where's my history? I can create a bundle file, and I'm creating it inside that directory. So this is git bundle create. The file I'm creating is a fixed file name because my little hook assumes a fixed file name, and I want it to pack everything that's under branches or tags, which corresponds exactly to what goes in a normal clone. This also takes a while. This is doing roughly the same job actually, because it has to enumerate and count. Okay, I should have just kept that file and not just deleted it earlier.
That's okay.
Sorry about
I have
that.
a question. So one of the things we're discussing about this is the disk storage requirements, and obviously pre-computing and storing this requires more storage space.
Yeah.
But in this case, we're not actually storing a full copy. We're actually storing the stuff that you'd clone. So in the case of GitLab, where we store a lot of keep around refs and other sorts of data and history in the repository that may have been removed, this bundle should actually be smaller than the repository, although
yes,
in likelihood it's probably going to be close to the size of the repository.
Yes, exactly. I have no idea what the ratio is of how much non-reachable stuff we keep around, but I don't think it's very much, because most of the space is in blobs, and unless you have a lot of weird binaries that are not normally reachable, the blobs you are like you have a merge request and you create a certain file, and then that got rebased or something, but you probably had the same file in the end. Or you have a file that's very similar, so it delta compresses against what you already had. So I don't expect that stuff to add a lot of space, but I actually don't know. I do know that this base repo is not in a perfectly packed state, but let's look at that for a moment. So I can look at the objects used by the thing itself and the bundle. Wait, so I want the objects directory, and then I want the bundle. So in this case, it's a big difference, almost half. But I could run a git GC in here, and I don't know if I will be left with 790 megs or if it gets smaller.
And I guess the other thing to consider is, so if we're thinking about one repository, we're essentially storing it in duplicate. But for forked projects where there are forks, potentially like yours,
yes,
as long as there is one fork, like
you would only do it for the parent, and then you end up like no matter what you do with this approach, you risk ending up sending data to the client that they don't need.
Yeah.
but it's likely not a lot of data they don't need. And the flip side is that everything is faster. So yeah, so what is next? Yeah, and I'm just going to run the magic clone again. So that was that RMRF thing. So now I've created that bundle file, and let's see. So we were talking for a long time, and we were still in counting objects. And now we skipped straight into receiving objects, which is not going very fast, but I think this is basically limited by CPU and the disk I have on my machine.
And now you've bundled the same repository as you're cloning right now. What if you now add a commit to the original, like the normal gitlab.git, and then you clone? What happens?
Yeah, let me do that. So now I'm creating a tag in there, and that tag will not be in the bundle. So if I do this now, then it actually enumerates 2 objects. So this is a very silly simulation of what would happen when your bundle gets stale. Like in reality, if you leave it for a week, there might be hundreds or thousands of new objects. But on a repo that is as a total size of, so in this case, we're sending 900,000 objects, so you still save something. And the part we're looking on, yeah, so this, I think at this point, the network transfer is done. And the rest is Git analyzing the data it received.
Yeah. So essentially what we're doing is like, if we think about the numbers of clones, like we're trading like the fact that on a highly cloned or regularly cloned repository, we only have to do the calculation like at a lower frequency on the server side. So we're reducing the compute so that you get a faster clone, and we're paying for that in the storage.
It's a time versus space trade-off.
Yeah.
And I mean, in Git's defense, during a normal clone, there's already a lot of optimizations going on. The normal enumerating objects, counting object stuff, they reuse compressed data a lot already, but it's not the same as what this is doing. It's really pretending that somebody already cloned at the level of the bundle file, and they're doing a git fetch on top of that. And if you do a git fetch of a week's worth of data, that's always going to be faster. Well, not always, but if your repo isn't very far behind, that fetch is going to be much faster than a full clone. I can also show a little bit of how this works or how I did this.
That would be very interesting to me.
Okay, yeah. So I one day noticed a weird config setting in the manual page of git config called, let's see if I can pull that up. Back objects hook, this thing. So this is a config setting where instead of running git back objects, which is something that runs deep inside the server part workload of a nested clone, you can run a different program in its place that gets the original command as an argument, and it gets the same standard in that back objects would have received, and whatever it blurts to standard out and standard error goes back. So you're just replacing that thing, and I'm wrapping this git back objects thing. And the input of git back objects is it's just a list of the objects that the client wants, optionally followed by a list of the objects the client already has. So during a normal clone, the list of objects the client already has is empty. And what I'm doing is I'm using the bundle file, which contains a list of the refs and tags it contains, and I'm pretending, so I'm saying to pack objects, the client already has these files. And then the real pack objects only packs the difference.
Is this a hook which we could, so in storing that pre-generated bundle, is that something we could stream from object storage rather than being objects?
Yes, let me look for the file. would have helped if I had prepared this. Come on. So this is the, can I do syntax highlighting? Yes, wow. This is the main executable. So this first part is where we're scanning the input. And yeah, it uses the presence of this magic word not, and uses some part of the input structure to decide if it's a clone or not. And if it's not a clone, then it does a fallback to the normal pack objects. Mm-hmm. And otherwise, it opens the bundle file as a regular Go file, but then all we do is wrap that in a buff.io new reader. So if this, instead of opening this file, if this was an HTTP GET URL, then you get the GET response body, which is also an IO reader in Go. So you can just plug anything in, and this is all we. This is all the assumptions we make, so we don't have to seek in this file. This is a nice property of the bundle file, because a bundle file starts with the description of its contents at the top, and we use that description.
So basically, we could even tell Workhorse to do all the heavy lifting.
No, because this is a hook that runs inside git upload pack, and git upload pack runs on the. Yes, okay, we could glue. No, I don't. Okay. This is not, because the there's two parts. There's the bundle, and there's the little extra incremental piece on top. And we compute the incremental piece with information from standard input into this hook. And that information comes from git upload pack eventually. And git upload pack runs on the Gitaly server. So we would have to parse the git transport data ourselves in Workhorse and decide we're going to rewrite this and set something else at the transport layer. And then it has to go down through upload pack into pack objects. And
yeah, let's keep it in Gitaly.
I think this is the easier way to get there. Let me show you for a moment why the bundle file is helpful. It is a binary file, but it will load, I hope.
So just for like completeness, this relies on Delta Islands. No. This does not rely on Delta Islands.
No,
so
this
is separate to the Delta Islands work you're doing.
Yes, this is completely independent. There is a hint I'm seeing in the implementation of Delta Islands that suggests that if you're using Delta Islands, then the pack file we need here, this bundle file. But let me get to that. So the bundle file has two parts. First is this, which is commit IDs and ref names. And that's exactly what I need to lie to pack objects and say the client already has these objects, and I can just read this list of objects from the top of the file. And then after that becomes binary pack file data. So this is in exactly the right shape to pull off this trick without having to seek or do anything. So these are the two ingredients you need. You need these object IDs that describe the pack file, and you need the pack file itself. Now, what I think is going on with Delta Islands is that if you do a repack with Delta Islands and you do it right, then the first X bytes of your resulting pack file are actually the same thing as what we have here. So, but you need to know what X is, like how many bytes into the pack file do you need to read to get this sub pack file. Plus, you need to know what are these object IDs that describe this sub pack file. If you know those two things, actually, if you know the object IDs, you can, no, you need to know those two things, then basically you could generate the bundle file on the fly by reading from a pack file that you need anyway. I think that's what I'm saying. So then this whole storage problem goes out the window because we have the pack file on disk anyway on the server. And if we have this extra metadata that describes the special initial segment of the pack file, it's as if we have this bundle file sitting next to it.
Okay, so in combination with Delta Islands, if we do this right, we might not even have the extra storage requirement.
Yes, but the thing I'm not sure about yet is if the way Delta Islands is implemented now, we have enough information to find this hidden embedded pack file. Because if you're in the middle of the Git code that is generating the pack file during a repack, you know where that part ends and the rest continues. But to piece that back after the fact is not entirely obvious.
Okay. So that's really amazing. In the short term, it sounds like we should put this behind a feature flag so that we can enable it on a project by project basis and experiment with this so that our storage requirements for all of GitLab.com don't go through the roof, but we can start testing it and like verifying the performance improvement on some projects on GitLab.com. And then I guess we can look at the different approaches for mitigating the storage increase, either by trying to work out a way to use Delta Islands to get it for free, or potentially using object storage, which might be a more generalizable solution for some of the bundle situations we might want for partial clone, where we will have like different pack file or different bundles for different situations.
And it's also cheaper than storing it on block storage, probably. And you have a bunch of nice properties, like you could say, depending on your object storage provider, you may have the option that old files expire. So you can say, we create these things, but if repos don't get accessed a lot, then we expire their pre-computed bundle file eventually, and we keep the storage. I mean, on GitLab.com, that would reduce the storage cost tremendously. Yeah, if we want to start doing this behind a feature flag, then there's two things. That hook executable that I made needs to be cleaned up and included into Gitaly and into the omnibus config. And it does nothing if there is no file called clone.bundle. So we can just install it globally and leave it there, and it's transparent. And then the only thing that we need on top of that is to have a special RPC that can create those clone.bundle files on demand, or some mechanism where we can say this repo gets a new bundle file now, or
can we do it in the garbage collection?
We could pile it on top of that. I mean, I would still put it in a separate RPC, but we could schedule it. Okay. We could use the same scheduling mechanism and say, when we do this, we also create this extra file, and then it would be a flag. Yeah.
I got another question. This bundle, I just asked about edit objects, and now my question is, what if we delete a branch which has a whole lot of objects?
The client still gets them.
Yeah, and the client is fine with that and just disregards them, removes them locally, or I don't know actually what.
They become dangling objects on the client side.
Okay.
So the next time the client, I don't know. That's up to us to. That's a question, but if it's not a lot of objects. Yeah, I mean, you get. I think it happens in normal use, because if the client would have actually done a fetch at the time that the bundle file was created, it would have those objects, like if it would have cloned then. Yeah. And if a week later does a fetch, then it has some dangling objects. So it's the same situation. If the bundle file is very stale, it gets progressively worse. But on the other hand, Git clients by default run gc.auto automatically. So there's mechanisms in Git anyway to sort of manage this.
Are there like James and I just understand this topic, I guess, but you've worked with this. Are there any other downsides other than storage? It seems like such an not such an easy win, but more like such a big win that it seems too good to be true.
Yeah. No, I think so. It's the storage cost, and you're serving stale data. I think those are the downsides.
Yeah,
There's a
maybe
trade-off that has
yeah.
to be made between how frequently you update this bundle file and like the upfront work of doing that. So in like a low traffic repository, you might end up generating a lot more bundles than, so like burning a lot more CPU cycles than otherwise would have been burned by someone just cloning it once a month. And then you've got the storage cost as well of like storing potentially all this extra data just to accelerate one clone once a month.
And you're also only accelerating a full clone. If somebody does a partial fetch, this thing gets out of the way and does nothing. So then you fall back to the normal situation. If somebody does a partial clone, I think in CI we do a lot of partial clones. Sorry, shallow clone, where you have limited history depth. That also completely bypasses this. So you're investing this big space cost to accelerate exactly one type of request.
Yeah. It would be interesting to do some analysis around shallow clones, because I assume we could be more smart and improve the sophistication of the hook to, I guess, pre-compute something that is more useful for like a shallow clone. Because I assume that like the delta between the head of master and the head of a feature branch or whatever is being tested is going to be relatively small.
No, yeah, I agree. It's probably possible to do that as a special case.
Yeah, but the performance improvement may not be worth it at that point, because in a shallow clone where you're only doing a depth of 10, you have a much
actually it may or may not. Shallow clone is not. I think shallow clone is not necessarily cheap. I mean, what's cheap about shallow clone is the amount of data you send. But the problem is that, because, as I understand it, is that the way pack objects works, or the way Git works, it tries to avoid sending data that the client doesn't need. So if the existing packed object is arranged, packed data is arranged in such a way that it would include objects that do not belong in the shallow clone results, Git will actually start making an extra effort to not send those objects to the client at the expense of CPU and IO on the server.
So we could make shallow clone a little bit more like greedy in terms of the amount of data it transfers, like sends more data than it needs, and then that reduces the amount of work needed to like send the delta.
Maybe. I don't really know how the scales end up between what you save, and because the other downside is that if you feed the wrong information into the real pack objects process, it actually takes longer. In the first iteration of this, I just thought, okay, I'm just going to take a chunk of a pack file, and I can use the index to just get the object IDs. So I just had a random selection of objects, and I said during a clone, I would say to pack objects, I want this, and by the way, I have this random really long list of a couple 100,000 objects. And then pack objects became very slow. So that was bad. And what's nice about the bundle scenario is that there are 900,000 objects in that bundle file, but that list of refs at the top is not 900,000 objects. And I don't know the details, but my suspicion is that if the list of halves is too long, it may slow down pack objects. So in the case of, I suspect with the shallow clone, it would still be okay, because the shallow clone would be computed at a certain commit. But if you're very unlucky, that commit is more than 10 commits ago, and then Git says, okay, you have a commit 20 commits ago, you want the last 10, and now I'm just going to do that stuff in the middle and not reuse what you have over there. We'd have to experiment to see if it's beneficial.
Yep. Thank you for this demonstration and explaining that.
You're welcome.
Saw your link to the issue earlier, which I'll take a look at, and I'll probably cross-link it and create a few more issues based on this conversation. This is very exciting.
Cool. Thanks. I'm very enthusiastic about this myself, and I've been sitting on this for a while but I was too busy doing other stuff. And you asked me the question yesterday, James, or I said something, and then you asked the question, and I said, okay, I better put my money where my mouth is and prove if I can do this or not, or if we can do this. And we can.
Well, that was a worthwhile experiment. I've got to
also, no.
Oh.
Yeah.
Oh, this also increases visibility. I'm super excited. Yeah, good stuff.
Cool. Thanks.
Thank you, everyone. Bye.